Good morning, good evening, depending on which part of the world you are. My name is Alessio Roccon, and I will chair this session. So today is a great honor to have here Professor Zhengmao Lu, who is assistant professor at the Mechanical Engineering Department at the École Polytechnique Fédérale of Lausanne, where he leads the ITA lab. His research focuses on interfacial phenomena, and in particular on transport phenomena at the interface, like phase change. So before joining EPFL, he was postdoc at MIT in the Department of Material Science and Engineering, and he also got his PhD and a master from MIT. So in today's talk, he will give us some useful insight on interface engineering for high-performance cooling application. Please, stage is yours.
Thank you, Alessio, for the nice intro. So again, I'm Zhengmao. So I joined EPFL last year. We're trying to build up a lab that does heat transfer and phase change phenomena here. Today, the majority of the work that I'll be talking about is still going to be the work done with my PhD and postdoc advisors. Towards the end, I'll briefly speak about what we are one topic that we're trying to work on, kind of extending from the existing project. And my primary research interest is interfacial transport phenomena, and I'm especially interested in the application to cooling. So the title today is Interface Engineering for High Performance Cooling Across Scales. And there are two types of cooling applications that I want to talk about today. And the first one is regarding the chips for electronics cooling. And so this is trying to dissipate large amount of heat over a small area. So in this schematic, I'm trying to put the heat flux numbers of these electronics chip into perspective. So you can see it can go all the way from around 100 watts per centimeter square for the CPU or GPU chips. And for power electronics, the number can be even higher, above 1 kilowatts per centimeter square, even approaching the heat flux that you would expect at the sun surface. So for a heat transfer system, or like most of them, there are usually two things that you care about. One is the maximum capacity, the maximum heat flux this cooling system can deal with. So if you receive a high heat flux, like is your cooling system going to fail? And this is more important for the power electronics, where the heat flux dissipation requirement is more extreme. So people have been pushing the cooling performance to kind of take care of the higher heat flux, like above 1 kilowatts per centimeter square. So that's one important metric. And for the more commonly seen, like CPU and GPU chips, those who are sitting in the data centers, the heat flux dissipation requirement is not as high. It's still pretty high, like much higher than the heat flux you would expect from a stove oven, for example. But we have quite a few options to cool those things. The important point there is cooling is consuming a lot of energy in these data centers. So if we can have a cooling solution that cools things efficiently, like using less temperature rise to cool the same thing, then there can be energy saving opportunities. So I'll speak a bit more about that later in the talk. So the two things that we carry out, to summarize, is one is the maximum heat flux that you can dissipate, and two, how efficiently you can do that, or what's the heat transfer coefficient. And in the community, there are two types of cooling solutions people are pursuing. The left one, I'm showing a single phase like cooling example. So this was actually from one of my colleagues at EPFL, Professor Alison Mattioli's group, who a few years ago published this paper in Nature. Basically, they were able to bring the microchannel cooling solution very close to the in-house gallium nitride chips that they were making. And just by shortening the distance between the actual cooling and the device, they were able to dissipate large amount of heat with very small amount of temperature rise. And I remember the heat flux was approaching 2 kilowatts per centimeter square. So that was indeed amazing. And the second type on the right is about two-phase cooling. And the idea is that when phase change occurs, you can take advantage of the large enthalpy of vaporization without incurring large temperature rise across interface. So if you can manipulate the interface with novelly engineered materials, then there's a chance to get high heat transfer performance. So the example was from Professor Ken Goosen's group at Stanford, where they were using porous materials basically to magnify the interface area and minimize the thermal resistance within the materials, a technique that I'm going to talk about later in this talk as well. So whether it's single phase or two phase, people observe that when it comes to the choice of the coolant, usually water gives you the best performance in terms of cooling. But if you're an electronics person, likely you would not feel very comfortable putting water very close to your electronic device for obvious reasons. And to boil it down to, it's really about the dielectric strength or the resistance to electrical breakdown. So here we have this dilemma between the cooling performance and the dielectric strength. So as a thermal person, I don't know much about how you can improve water's dielectric strength, but at least we can look at why water performs so well from a thermal perspective. So the primary reason that water usually is your best working fluid in either two-phase or single-phase system is about its thermal conductivity. Here in this table, I'm normalizing the thermal conductivity of a list of working fluids to the value of water. And clearly, water holds the advantage by having the smallest thermal resistance in the liquid because of high thermal conductivity. In single phase, apparently the liquid thermal resistance is important. Even in two-phase systems, in most of them, it is still the liquid layer thermal resistance that dominates overall transport. If you actually analyze the evaporative transport for vaporization and apply the kinetic theory to the molecular gas dynamics near the surface, it's not that difficult to derive a figure merit for evaporation itself. And this ends up being the product, as I'm showing here in red, the product of the equilibrium vapor density at the liquid surface, the speed of sound at liquid surface, and the enthalpy of vaporization. So this is almost like ejecting liquid into vacuum at the speed of the sound. And the product gives you the number or unit of watts per meter squared of the unit of heat flux. And although water has a very high enthalpy of vaporization, because the vapor density of water is usually quite small, and if you compute the numbers, again, normalize everything to the value of water, you see that water actually, in theory, has the worst pure evaporative performance. So this seems to tell us if we can build a device that minimize the thermal resistance in the liquid and makes the evaporative transfer actually the dominant part of the overall heat transfer, then not only we're going to reduce the overall heat transfer resistance because now the liquid part is getting reduced, but also in this system, we would expect the dielectric liquids, the low surface tension liquid, will perform better than water. So that will give us a chance to solve the dilemma. And with this in mind, first, let's try to find a basic working unit from which we can scale up with. And our basic working unit here is a nanopore, or if you have many of them, it will be a nanoporous membrane. And here in the schematic, you're looking at a small amount of liquid column contained in a pore with a meniscus pinned at the top. And if we somehow put the liquid there and somehow route the heat there, just because how small the pore is, the liquid thermal resistance in this configuration will be rather small. And so this unit itself, from the solid to the vapor, will have a very high heat transfer coefficient, very low thermal resistance. The question for us is, how do we get the heat to the membrane? And how do we route the liquid to the pore? So to do that, we have to design a microfluidic device, actually a hierarchical membrane device. So if you're looking at the schematic on the left, the top one, it has a green manifold channels, which is to supply liquid. So the liquid first enters these green channels. And underneath it, transversely, you have these microchannels in red running across, which is connected to the green channel. And then after the red microchannel, the liquid can wick into the nanoporous membrane, which was our working unit that we described in the previous slide, where evaporation will actually occur. And because we have this hierarchy of characteristic size between the green, the red, and the gray, we effectively minimize the pressure drop in the device, just like a tree. And if we're assuming we're taking heat from the bottom, if we're looking at the bottom schematic, the solid walls of these microchannels provides effective heat conduction paths to the membrane. So you don't have to go through the thick liquid layer within the channels. Instead, you can go through the highly conductive solid wall just to route the heat to the membrane, so this serves the purpose of taking the heat to the membrane effectively and routing the liquid to the membrane with minimal pressure drop. So after having this design, the first thing that I did is to create this nanoporous membrane and actually to test whether the heat transfer across this membrane is indeed what we expect. And to do that, so here I'm showing you a microfabricated ultra-thin nanoporous membrane. We have two gold contact pads connected by a suspended area. So this area is where we have the suspended membrane in the middle. And if you zoom into that, at the center, we have an active region, which is nanoporous and also covered with gold. So this whole like almost transparent area is around 200 nanometers thin, and only the very center, we have the pores, we have our metal layer coating the top. So this metal layer will end up serving as both a Joule heater and a resistive temperature detector. And during the experiment, we'll route the liquid to like underneath these membrane and use wicking for the liquid to enter the pore spontaneously through capillary action. And we pass current through the metal layer to provide heating to induce evaporation and also to maintain a steady state and measure the temperature with its resistance. So roughly that's how the device operates. And with that, we can test the heat flux across the interface as a function of the membrane temperature, which is very close to the interface temperature, that interface that's contained in the pores. So the y-axis is the heat flux across the interface normalized to the pore area, and the x-axis is the temperature difference between the membrane and the far-field vapor, or far-field, in some cases, far-field air. So the purple data points are from our experiments, indeed in the ambient air, where you expect evaporation to be diffusion limited. The vapor generated from the interface have to diffuse through the air molecules. And the red data points, they are from the vapor ambient data, where we assume the evaporation is kinetic limited. So it's a vapor kinetics that's dominating the transfer. So it's not that surprising that the red data points have a much higher slope or much higher heat transfer coefficient compared to the purple one in air, because by having a pure vapor environment, we are eliminating the diffusion resistance. The other thing that we observed was that if we elevate the vapor ambient temperature and still plot the q dot double prime, the heat flux as a function of delta T, we see that with the same delta T at a higher vapor ambient temperature, our heat flux also gets higher. So higher system temperature seems to lead to a larger interfacial heat transfer coefficient. And we thought that was interesting. So we came back to the theory that dictates the vapor kinetics near the interface, which is a highly non-equilibrium behavior if your flux is rather high. So we have to look at the Boltzmann transfer equation that governs the non-equilibrium molecular gas dynamics near the interface. And what we found out, also actually in previous theoretical analysis, we also pointed out that you can normalize your heat flux to these product of rho now US HFD, actually the figure marries for evaporation that we discussed earlier. And this gives you a normalized or dimensionless heat flux. And based on the Boltzmann transfer equation, it should only be a function of the normalized pressure difference. So P naught here is the saturation pressure at the liquid surface, and delta P is just the difference between P naught and your ambient far-field vapor pressure. And so the information of the BTE of the Boltzmann transfer is contained in these functional form F, and sigma here is actually your boundary condition. So the physical meaning here is if you have a molecule approaching a surface, the sigma signify the probability of this condensing into liquid instead of being reflected away. So with this analysis and given this experimental data, we can convert our dimensional data here to dimensionless data without making additional assumption. And the result of that is that all the data from different working conditions now collapse onto one single line. And this line should be a result of the Boltzmann transfer. And so with the collaboration from Professor Ikuya Kinofuchi at University of Tokyo, who is an expert in numerical simulation for Boltzmann transfer, so using the direct simulation Monte Carlo method, they're able to fit a sigma, a condensation probability, like with the Boltzmann transfer, to generate the dashed curve. So this dashed line is like not just a regular fit, but it's like solving the Boltzmann transfer using sigma as a fitting parameter. And one thing I'm extremely or especially excited about is this clap itself. So the fact that the experimental data from different working conditions collapse to this one single parameter like curve suggests that we are indeed in a kinetically limited evaporation regime, such that it's really from the evaporation of the membrane, it's really the vapor transfer that dictates the overall like heat transfer behaviors that we're observing, which is the reason that we designed the device this way. So going from this membrane device to an actual cooling device, there are actually a lot of other things to do because we have to create those manifold channels. And for that part, it was actually my lab mate, Dr. Daniel Hanks and Dr. Jay Sarkar, who took the lead of creating this hierarchical cooling device. So I'm just going to present their effort. The fabrication scheme is like this. So in step A, we start with a SOI wafer that is a thin device silicon layer with a buried oxide layer between, and then on the bottom, there's a silicon handle layer. So silicon oxide, silicon from top to bottom. And with interference lithography, basically using interference pattern as your mask, you can create large area of nanoporous patterns that first like etched into the silicon device layer on the top. And separately with another wafer, so looking at the middle schematic, we use the cleanroom like stepper machine to create these microchannels with 2-micron feature sizes. And then we can use silicon fusion bonding to bond those two pieces together to form a hierarchical device. And then with deep reactive ion etching, we can etch from the top to open up the vapor escape channel. So this is how the fabrication look like, and eventually this is the device that you get. So with this device, we can do some thermal testing, but first we have to pattern some heater to the backside of this device. And so here again, you're looking at some joule heaters and some resistive temperature detectors allow us to provide heat to the membrane device and also measure the temperature at the bottom. So this is to simulate to the electrical thermal load. And then an environmental chamber was built to create the pure vapor ambient for different type of fluids. So that's what we're going to test. Then we can report the heat flux basically as a function of the temperature rise between the vapor in the chamber and the backside of the device. And to interpret the experimental data, I actually built a 3-tier model. So from the interfacial transport across the evaporating surface, using the Boltzmann transport to describe the non-equilibrium vapor-gas vapor dynamics near the evaporating surface, and then putting that as a boundary condition for the unit working cell in the device, and then eventually to scale up to the whole device. So later, or in the next slide, I'll show the experimental data together with model prediction. So here, the y-axis, as I said, is heat flux normalized over the whole device area. And the x-axis is the temperature difference between the backside of the device and the vapor in the chamber. And the data are for R245FA and pentane, two quite dielectric liquids. And what I want to highlight here is that these data points, around 500 to 600 watts per centimeter square, still represents, to my knowledge, the highest pure evaporation heat flux for dielectric liquids without spreading. So this, to us, was very exciting because it was the first time such high heat flux was achieved just with evaporation for those type of liquids. And what was more exciting to us was that after testing a list of other fluids, including methanol, IPA, and water at different temperatures, you can argue they have different thermophysical properties, we see that in general, the low surface tension, high volatility dielectric liquids has a higher heat transfer performance in this type of cooling device compared to water. And we expected this because we are minimizing the thermal transfer resistance in the liquid. So the thermal conductivity becomes not so important as a criteria for heat transfer. So this gives us, I think, an opportunity, if we further optimize this, to address the dilemma about the coolant choice in the electronics cooling systems. A few things, or a couple of things that we still need to work on. One is that, as you can observe, the experimental data starts to deviate from our model prediction at high temperatures or high heat fluxes. And we think this is related to the contaminant aggregating in the pore. So because we are having a pretty high velocity of liquid in the pore because of the small area, this is actually bringing in any trace amount of the contaminants in the bulk liquid quickly towards the evaporating surface. And one evidence that we saw in this picture or in these two images is before and after the pores, we do see some something like accumulating on the nanoporous membrane that is our major functioning unit. So this is something we need to circumvent with our design. Basically, we need to allow more flushing underneath the membrane. So that's one. And the second comment is that this is only the evaporator. And to complete the whole heat dissipation, we also need to perform the condenser side heat transfer study. So this is an ongoing study that is happening in my group right now. So we have a project on this. And for this electronics cooling thing, previously I was commenting that if you can cool things more efficiently, there will be energy saving opportunities in those data centers where all the hot chips are hosted. So the reason I was saying this is that if you look at how the cooling occurs in a data center, you have a cooling loop. Basically, you have some cold fluid going in, hot fluid going out. And the heat that was dissipated into these cold fluid, typically they're of low exergy or low grade heat, very hard to use. So sometimes people are trying to use this for district heating. So that's one way to harvest that waste heat. If we somehow can apply our efficient cooling solution to these chips, which is indeed dissipating a lot of heat, we can have the opportunity of using less temperature rise to dissipate the same amount of heat. As a result, we can have the inlet of this cooling loop towards the data center at a higher temperature. And this is so-called warm water cooling. And with warm water cooling, your outlet will be at a higher temperature. So you have a higher grade heat to do waste heat recovery, which would be easier and of higher efficiency. So at EPFL, we actually have a program called the Heating Bits running exactly on this idea. I guess the key difference is that the heat recovery part, so I think what they were proposing, the team was proposing, was using an organic Rankine cycle to leverage or to recover that waste heat. So to be transparent, I'm not part of the team, but it will be very exciting to see what can come out of this. I think the project just gets started, and you can check the website if you want. So with that, I think that transitions us well from a chip level cooling to more like system level consideration. So cooling is not only a chip problem, it's also a system scale problem. Here I'm showing a graph, basically the prediction from International Energy Agency, trying to predict how much energy would consume for cooling over the years, so between now and 2050, if we don't do anything about the cooling efficiency, then their conclusion is the cooling energy demand will just double. And the thing about cooling is it can fuel a vicious cycle if you have increasingly high cooling demand, because you will build more air conditioners, for example, to address this cooling demand, and this can incur more carbon emissions, and this may accelerate global warming, which will make your cooling demand increase more. And so apparently we have to do something to address this vicious cycle. And the one promising way to do this is using 3K outer space as your thermodynamic cold source, or using passive radiative cooling. So our Earth's atmosphere has two types of transparent windows for electromagnetic waves. So one is in the solar spectrum. This is why we see the sunlight going through the atmosphere without too much problem. And the other is in the mid-IR spectrum, where if you are emitting at that spectrum, it can transit through the atmosphere also without much loss. So this is indeed how the Earth is cooling itself, because if you're looking at the black body spectrum here, the red dotted line at 300K, which is apparently or approximately where we are, the radiation from the Earth's surface at that temperature can actually go through this window quite easily. And the problem we're having with global warming is the CO2 or other sources, they are contaminating this window. But that's a story for another day. So today, the goal here is to engineer a surface that can radiate in the spectrum so that you can do direct heat transfer with the outer space, which is much colder. And at the same time, since it's going to be facing the sky, to avoid being solarly heated by the sun, the surface also needs to be solar reflecting. So at the end of the day, your net cooling power will be the radiant cooling power minus the solar absorption minus the atmospheric emission to you that's being absorbed. And depending on whether you are higher or lower than the ambient, you can have parasitic heating or parasitic cooling due to convection. And I think for the past 10 years or so, the radiant cooling community is really booming. And ever since, I think, the first demonstration of passive daytime radiant cooling from Stanford and Shanghui Fan's group, there have been a lot of materials developed. Some of them are more scalable than the others. But the basic idea is the same, that if you have a surface that can radiate mid-IR and reflect sunlight, net cooling can be generated. And in 2020, there was this review paper calculating the radiant cooling power for ideal radiant cooler that is totally solar reflecting and totally IR emitting. And even with that condition, we see that, at least at the ambient temperature, the cooling power is still limited by 120 watts per meter square. So this can be good already for a lot of applications. The problem is, one, you need a lot of area if you are limited by the 100 watts per meter square to do something useful. And two, this thing is very sensitive to the weather condition, as we'll see later in my experimental data. So my idea at that point was to integrate radiant cooling with some other passive cooling methods to keep the passiveness there, but to improve the cooling power. And a good candidate for integration there is the evaporation or evaporative cooling. So this is why we were developing this thing, insulated cooling with evaporation and radiation, or ICER. So obviously we went for the acronym, but the goal here is to integrate the evaporative and radiative cooling method to get higher cooling power. And we want to integrate it in a synergistic way. So the cooling channel, they can be parallel and not interfering with each other that much. For example, if you just slap a water layer on top, then the water layer will be absorbing a lot of sunlight, which is not what you want for radiant cooling. So here is how the architecture look like. From bottom to top, first you have a solar reflector that is reflecting whatever sunlight that will going to reach that surface, which is not going to be a lot. And in the middle, we have basically a water layer that will do evaporation and also IR emission, because water has pretty high IR emissivity. And on top, I'll say that's the key functional unit. That's our insulation layer. So it does two things. It's insulating this device or this cooling stack from environmental heating. So this environmental heating includes parasitic heating if you are below the ambient temperature. So it has very low thermal conductivity. It's also insulating this from the solar heating. So it has very high solar reflectance. And the second role it plays, it has to allow the cooling channel to be open, basically allow vapor to go through, allow IR emittance to go through. So it has high IR permeability, high IR transmittance and high vapor permeability. So in theory, how this should function is from this evaporator plus emitter, you have vapor and IR coming off, and this goes through the insulation layer without much loss, and this dissipates the heat, whereas your solar heating and the environmental heating in a parasitic form gets rejected away. The question remaining is about the materials. For the solar layer, solar reflection layer, so we have the option to use the radiative cooling material that is a 3M ESR film, enhanced spectral reflector. So it has very high solar reflectance and is often used as a reference radiative cooler in radiant cooling devices. But in this case, we're just using this solar reflectance. And for the evaporation and insulation layer, so for the compactness of the lab test, we have used hydrogel for the evaporation layer. So indeed, it can be any hydrogel with high water capacity. So we chose the polyacrylonitrile hydrogel. And for the insulation layer, we end up synthesizing this polyethylene aerogel, which is a pretty low thermal conductivity, approximately the same value of static air for its thermal conductivity. And importantly, if we're looking at the optical properties in this visible spectrum, the PEA, or the polyethylene aerogel, is diffusively reflecting. So this is white or opaque here. And the hydrogel is transparent. So this means there's limited solar absorption here, and most of the solar incoming radiation will be reflected away from the insulation. And in the IR spectrum, the hydrogel has very high emittance, so which is why it's opaque. And the aerogel, the polyethylene aerogel, is almost transparent. So the IR emittance from the hydrogel can go through the insulation layer without much loss, which is exactly what we want. So with this material stack, we can design or develop a model that captures the mass transfer governed by the fixed law of diffusion in the aerogel from hydrogel across the aerogel, and the fixed law for thermal conduction across the whole device. And importantly, the radiated transfer for both the IR and the solar spectrum, accounting for the variation of intensity of the radiation as a result of the outscattering, inscattering, absorption, re-emission, and plus the solar irradiation. So later, I'll present the modeling result together with our experimental data. In terms of the experiments that we did, the first thing was a stagnation temperature test. Basically, we wrap around this cooling stack with insulation, and the idea is to simulate a 1D heat transfers easier for us to understand. So by having the surrounding, having insulation around, it becomes almost 1D. The left is our ICER design, so a ESR reflector plus a evaporator plus insulation. And the left-hand side is basically just slapping a water layer on top of a reflector. So it's an evaporation dominated cooling. And if we monitor the temperature as a function of time from 10 a.m. to 10 p.m. on a summer day, this was in Cambridge, Massachusetts, the black line here is the dry bulb temperature. So that's the environmental temperature. And the gray line is the wet bulb temperature. Our orange line is the evaporation dominated cooling sample, which is already showing a respectable amount of cooling. And the ICER, the blue, is staying at even lower temperature. And importantly, it's consistently below the wet bulb temperature. So that's the lowest reachable temperature with evaporation. So it's certainly better than pure evaporation. And compared to the orange sample, so the temperature difference is not that much. Actually, it diminished during the night. But if you look at the water consumption, the ICER can reach lower temperature even with less water consumption. So this is like having your cake and eat it too. So this is what gets us very excited. So this graph shows the advantage compared to an evaporation dominated approach. And compared to a pure radiated cooling, what we did was we embed a heater in the cooling stack and compare this to a state-of-the-art radiative cooler. What we're plotting here is the cooling power, that's the power you put into the heater, as the function of the steady state temperature relative to the ambient. So we put a certain heating power there, and we measure the temperature of the cooling stack, and delta T is this temperature relative to the ambient. So 0 is where ambient is at. And we see that at the ambient temperature, we have 300 cooling power enhancement from the pure radiative cooler, if you're looking at the number for the ICER. And this was done at a unfavorable weather condition. So the 80 or to 90 watts per meter square was delivered by ICER at a not so favorable condition for passive cooling in general because of the humidity. So one note to make here is that the radiative cooling power that we are reporting here is much less than the typical literature data. And that's because in typical literature data, the RH is usually quite low, around 20% or even lower. And because water absorbs some of the IR emission, so if you have a humid day, the atmosphere is not that transparent in the mid-IR transparent window. And that's why in the pure radiative cooling, with when the RH is high, the cooling power is not that useful anymore. While for ICER, because you have evaporation to help you, you still get around 90 for the ambient cooling power. And if you can move 1 degree above the ambient, it can even reach 120. So that's already the highest cooling power an ideal radiative cooler can do. So hopefully with this data, at least on the device level, I can convince you that the ICER holds a lot of the potential. And then if we think about the application of such kind of passive cooling method to building applications, then we have to find a way to translate this device level cooling performance to building energy savings. And in the radiative cooling community, there are two types of methods like doing this. One is directly put radiative cooling coating on the roof and call it a day. So because you are making the thermal load of the building smaller. But this has an intrinsic problem with the evolving design of the building because modern buildings, they are designed to be insulating. So if you have an insulating building envelope, then doing things directly on the roof is not going to be that helpful, which is why a few other groups, they have this idea of running a cooling panel underneath your radiative cooling coating or plate and use that to generate cold fluid. And this cold fluid can be routed to any hot source in your building. And typically that means a condenser in your air conditioning system. So this way you can kind of circumvent the insulating building envelope to make the best of your cooling. And this is also what we are trying to do like now, and we already did some simulation. In this case, I'm simulating the energy saving for a model supermarket with a DOE like prototypical building. And the conclusion that we're showing that with 10% of the roof covered by the ICER, these type of cooling panels, you can already have a pretty nice annual energy saving in the majority part. This is showing every county in the United States based on its local climate zones. The other question that's important to ask is because radiative cooling is requiring sky access, so it's basically competing with the PV technologies. Because on one hand, you can save energy by sending heat to the sky, to the universe. On the other hand, you can use the same area facing the sky to generate electricity with PV. So in this plot, we are trying to compare the saving approach with the generating approach with the same type of setting, supermarket. And we pick a city, Miami, which is hot and humid. So typically not so good for passive cooling. And with ICER, we show that if you compare this direct like passive cooling case to using a solar panel to drive some benchmark AC, we are assuming a pretty high COP for this bench high AC. We can compare the like total cooling electricity saving. And if you are below 20% roof coverage, you can make an argument that the ICER can still outperform a premium PV. So I'm kind of painting rather like rosy pictures here for the like adoption of the radiative cooling method and or hybrid radiative and evaporative cooling method. There are two additional problems that we want to solve. One is that where we get the water. So although I claim that our evaporation layer consumes much less water, it still needs some water. So for that, we need to think about how we supply the water, even a small amount, to the evaporation layer. And apparently, a group of people have thought about capturing this water from the atmosphere when your thermal load is low, so you can do ambient water harvesting to get very pure water to recharge your evaporation layer. So that's one direction also we're working on. So I'm working together with another professor in material science in this topic, trying to optimize the kinetics for this like vapor recharging. And the second thing is about the robustness of these highly sensitive like radiative cooling coatings, because the optical properties is everything here. And when we started doing testing for these cooling panels, this was with the standard ESR films, just after a week on top of EPFL building. So I think the air quality here in general is pretty good. But after a week, this is what you see. And sometimes you see birds even doing something there. And so that poses the problem of the robustness, durability of this type of approach. So we have been trying to develop or follow some of the recipes that doing anti-aging cooling paints. And we had some initial success, like creating the good optical property, super hydrophobic radiative coolings. And we're in the process of testing this. And I think due to the limited time, I'll speak very briefly about this part. So basically, we're trying to create our own long-term outdoor radiative cooling platform. And by measuring the flow rate and the temperature difference between inlet and outlet with a radiative heat exchanger, we can characterize the radiative cooling power in a more realistic sense. And by having the remote control like buried in a waterproof like electrical cabinet and having it sit there for like long term, we can really see in a real world testing situation whether this robust cooling paint is actually robust. So this is just to show our preliminary data, like testing, basically showing that our cooling panel can indeed suggest that if you have radiative cooling films, it will cool better. So very briefly about the data here, this is monitoring temperature as a function of time for two cooling panels that we built. And we purposely make the working fluid a little bit above the ambient temperature. So you have convection and radiative cooling helping you both. And the left is a control group with a aluminum mirror. And the right is your ESR film where we expect some radiative cooling. And the area we're showing here is the difference between the inlet and outlet temperature. So with the ESR film with additional radiative cooling, you can see that there's a much larger area in terms of the temperature drop from the inlet to the outlet. So this is kind of where we are. We have the platform to test things a long term, and hopefully this summer we get to test some of the radiative cooling paints that we're also developing in the lab. And overall, so this represents one of the things I'm working on, and some other things I'm interested in across different scales. One thing is about the boiling bubble dynamics. I think a lot of people here are interested in that as well. And a few other groups reported this bubble collapse behavior during boiling. And I'm very interested in the phenomena and trying to understand the thermal implication of this phenomena. And the other thing that briefly mentioned about the condensation coefficient or condensation probability, want to develop new metrologies to understand how the molecules interface will actually interact during the evaporation and condensation process. And with that, I would like to summarize. So basically, we talked about two types of cooling. Electronics cooling, where you want to dissipate heat at high flux, but over a small area. And the building or system level passive cooling, we're trying to scale up the passive cooling panels and use normal materials and manipulate the interface for its optical properties to do cooling for you. And in the future, I hope to see the synergy between the two, because if you're cooling a data center, you want to do cooling from the chip all the way to rejecting that heat to ambient or to the sky. And with that, I would like to acknowledge my postdoc and PhD advisors and my key collaborators and also students and postdoc in my group. And thank you. Hope it's not too long.
Thank you. Thank you for the very interesting presentation across different scale. I think we can open the floor for a question. We can write them, I think, in the chat or just unmute yourself and directly ask to Zhengmao. Do we have any question from the audience?
Zhengmao,
Yes.
I'll ask the first question to break ice.
Okay.
I'm a great fan of your work. So first of all, I want to say that every time I listen to your talk and learn more things, and it's a great pleasure. Now, I have also questions, like as you may expect. So if you go to slide 11, the one on the evaporator. So if I understand correctly, this is operated with the, say, vapor in saturation condition, right?
Correct.
I wonder whether this can be simply explained by considering the effect of vapor pressure on the curvature of the liquid vapor interface at the orifice. Because somehow you have an equilibrium interface, and that essentially the angle formed by the liquid phase with the solid will be determined essentially by the vapor pressure here. Okay, I'm assuming that you have pinning on the mouth of the orifice.
Yeah.
And so to me, I'm not really surprised that in the end, increasing pressure on the vapor phase increases the heat transfer rate, which is, in my view, proportional to the contact line density. So practically speaking, to the number of the orifices and the diameter of the orifices.
That's a very good question. My response to that is the interface shape rather than determined. It's right. You're right. It's determined by the pressure difference across the liquid and vapor, and we're increasing the vapor pressure. And the way we are supplying the liquid is actually from the same canister. So the bulk liquid and the bulk vapor in our system, they share the same pressure. And the pressure difference between the liquid and vapor at the top of the pore is mostly a result of the viscous loss in the pore. So imagine you have a canister that has both vapor and liquid. So the vapor is going into your environment chamber and liquid goes into the device. And the pressure difference, actually, we can calculate how much is it. And if we use that pressure difference and just simply apply a Young-Laplace equation to look at the curvature, expected curvature in the pore, so we did that calculation, the interface is almost always flat just because how small the pore is. So yeah, I think that would be, that's how I think the interface shape itself cannot explain everything here.
Okay, so I think I kind of agree with you that the interface will, if indeed it's a kinetic pressure only, the interface is going to be flat.
Yeah.
And so it's very limited delta P that you have due to recoil vapor pressure. But now the question, did you try to check, your pore size are still very large, is in the order of 700 microns, right? So
100 nanometers, sorry.
100 nanometers?
Yes.
Okay, so you cannot say for sure whether you're limited by the area of the pore or the contact line.
Yeah, I think I'm more certain the interface is more flat than, closer to be flat than curved, just because how small the pore is.
Okay, thank you very much.
Yeah, thank you.
Do we have other question? Otherwise, I can.
There are a question in the chat? Or no?
No, mainly thanking you for the talk. I have one.
Okay.
Oh, there is one. There is one. I have a short question. How do you make sure there is no boiling happening at such high heat fluxes?
Yeah, the answer is the liquid is pressurized from the so the underneath the membrane. So it's like if I go to in these channels, those liquid are actually pressurized. So it's at a higher pressure than the saturation pressure at the surface temperature of these other smaller structures. And in the other smaller structures, you have the size scale that's helping you suppress the nucleation. So the way we can verify this is we don't see any pressure oscillation in our like liquid supply for this kind of microfluidic system. But the principle is basically pressurization.
I have a follow-up question, Alessio. I don't know
Yes.
if I
Oh,
can.
please go ahead, Matteo.
So what is the mechanism of failure here? Is it dry out or a nucleation in the liquid channels?
I think in our case, what I suspect is the way we design the channels, they have a dead point in the center where you expect the velocity to be close to 0.
Yeah.
And this causes a accumulation point of the contaminants if you have any.
Okay.
And because we are running things at a very high flux, this means it's going into that dead center very quickly. And
Mhm.
at least that's my theory right now, which I think the next step is really to have flushing like efficiently underneath these kind of membranes.
Because, sorry guys, I'm monopolizing this, but in this case, you're eating from the gold layer, but the actual chip will be heated from the bottom.
Yes, sorry, like I'm mixing things. So this is the
Yeah.
device that we are hitting from the bottom. So this
Okay,
is the
this is from the
device we are
bottom.
hitting. So
Okay.
this device hitting from the top to test the membrane performance.
Yeah.
And the other device was hitting from the
From the
bottom.
bottom.
Yeah.
Okay. Amazing. Thank you.
Okay, I think I have one short question. This is mainly out of curiosity. What was the temperature outside when you did the test in Cambridge? So MIT, I guess.
Yeah, I think it's in the data. You can
Maybe
take
it
a
was
look at it.
written in the slide, but I didn't read it, or
Yeah. So the dry bulb is
okay.
the temperature. So I think during that particular day, probably at noon is around 25 or so.
So it was kind of summer.
Like summerish, I guess.
Yeah. Okay.
Depending where you are. So yeah.
Depends on where you are. Yes. Okay. Do we have other additional question to the speaker? Otherwise, I think we can close the session. Please don't be shy. Okay. I think we can close the session.
Perfect.
And thank you. We can thank you again, the speaker, for the very interesting talk.
Thank
And
you.
I think with this, I think we can close the session and thank the speaker again. Thank you.